Welcome to the second session of our workshop, which was on quantitative data analysis. So yesterday we talked about, we discussed the basics of SPSS, how to import data, and how, for instance, you can prepare your SPSS data file before moving on to your hypothesis testing. So what we are going to today, we are going to talk about descriptive statistics part, that what are some of the descriptive statistics which are important to look at before you move on to hypothesis testing. And the second thing we are going to talk about is data cleaning. Because whenever you get data, there are certain risks associated with your data file. And before you move on to the hypothesis testing part, you need to make sure that your data is in right shape and right form. Now, some of the things which typically we look at while we do the data cleaning are, for instance, we look for outliers. Are there any outliers in the data set? Because sometimes the outliers, for instance, they result in biased estimates. So we check for outliers and we remove those from the data. Another problem which we typically come across with the quantitative data is the missing values. For instance, if you have like 220 respondents and there are like 30 respondents who have not responded on few of the questions. So if you remove those 30, you are going to lose a big chunk of your data set. So obviously, if you are dealing with a small data set, you won't do that because losing 30 respondents, maybe out of 100 or 200, that's not advisable. So in that case, we replace the missing values. There are different options and different ways of doing this. So a little bit we are going to talk about that as well. And another thing which is also part of data cleaning is checking data for a normal distribution. Most of the statistical tests, parametric statistical tests, one of the assumptions for running those is your data should be normal. Now, normal mean like you should have a distribution where the mean is 0 and standard deviation is 1. So, and your data distribution should follow a bell curve shape. We rarely see data in social sciences which is normal, but if the data should not deviate too much from normality. In other words, we can say that if your data is quasi-normal, you are still good to go, and you can move on to the next phase, which is hypothesis testing. So these are some of the things which you're going to look at, and we'll also talk about that if your data is deviating from normality, what you can do with your data to bring it close to the normality. So these are the things which we are going to talk about today. Okay. So first, I'm going to talk about the descriptive statistics part. Now, in descriptive statistic part, one important piece of information is frequency distribution, which means that how different data values in your data set, those are distributed, and what is their occurrence in the data set. So you can visualize a frequency distribution with the help of, there are graphical tools which are available in the SPSS. Like for instance, you can look at the histogram. You can also look at the bar chart to see the frequency distribution of your data. Apart from that, there are also tables which SPSS gives you in the output. You can look at those tables to see that what is the occurrence of each value in your data set. So this is the first thing which you would like to look at. The second thing is a skewness. Now, basically, the skewness is the measure of symmetry. And you may have a data set and this skewness is derived from frequency distribution. So if you look at the frequency distribution of your data set and you think that it's left or right skewed, then which means your distribution of data is not symmetric. So this is because skewness also tells you that whether your data deviates from normality or not, or how close that distribution is closer to a normal distribution. So and also SPSS gives you this the skewness value in the output. So there is nothing to worry about. You can just check one button or one click and you will get the skewness statistic. The third one is kurtosis. Now, kurtosis basically tells you that where your data is heavy-tailed or light-tailed relative to a normal distribution. So kurtosis also you can also look at the shape of your distribution. That will also give you some hint that what might be the kurtosis value or how your distribution looks like as far as kurtosis is concerned. Apart from that, SPSS gives you statistics for kurtosis as well. Now, the data which typically we deal with in social sciences, if we want that if skewness and kurtosis are within the range of plus minus 1.5, we assume that this is even for example, when you run the normality test on your data sets and you find data is non-normal, but if you look at the skewness and kurtosis and these two values fall within plus minus 5 limit, you are good to go. And you can move on to the hypothesis testing part. On the next slides, we'll talk more about this skewness and kurtosis. Okay, because I've been mentioning about the normal distribution, that why we look at the frequency distribution, because we want to see that whether our distribution looks like a normal distribution or not. Why we look at skewness and kurtosis, because we want to see that whether our distribution that looks like a normal distribution or not. The normal distribution, as I mentioned, which has a mean of 0 and standard deviation of 1. But that is an ideal situation. As I already mentioned, that in social sciences, we rarely come across distribution of data sets which are normal. Okay. So these were different pieces of information which are related to the shape of the distribution, the shape that how different values in your data set are distributed. Now, the other pieces of information which you look at are, for instance, the measure of centrality. Now, measure of centrality, for example, we may look at 3 values like mean, median, and mode, but mostly we are interested with mean. Like all statistical tests, which we are going to talk about tomorrow, those are based on the mean value, the average value, which we also discussed yesterday. Another value which sometimes you are interested in looking at is the median value. Median value, basically, if you arrange your observations, the middle value in your data set, that is the median value. For example, if you have 11 readings, so the reading which is at number 6, that is your median value. So yeah, the mode is the most frequently occurring value in your data set. For example, if you have 11 observations and out of 11, for instance, the 6th value is which is the highest frequency, or which is the most occurring value in your data set. So that is known as mode. But as I already mentioned, that mostly we are interested with mean. So we typically look at the mean value for our data set. The measures of variability, we talked about this as well yesterday. Now, variability, sometimes we look at what is the maximum value in our data set for that particular variable. Minimum value, range is maximum minus minimum, that gives you the range, and the standard deviation. So we just gloss over these maximum, minimum, range values, but mostly we are interested in the standard deviation. So mean and the standard deviation. These are two important pieces of information as far as descriptive statistics are concerned. Okay, so we were talking about the skewness. Okay, so as I told you that why we are interested in looking at skewness and kurtosis, because that tells us that what is the shape of our distribution. Now, for instance, if you look here, the two diagrams which you can see on the right side of the slide, kurtosis, you can see that is the peakedness of your distribution. So if it is too peak, like if you get a high peak in your frequency distribution, that you are going to get a positive kurtosis. And so normal is this. You can see this pink line, that is the shape of a normal distribution. We also call it the bell curve. And the negative is if the distribution is less than the peak of the normal. So that results in a negative kurtosis. And if it is higher than the peak of the normal distribution, that results in the positive kurtosis. Skewness, as I already told you, that measures basically the symmetry. Now, for example, if you look at these two shapes, which are here on the slide, one is the positively skewed and the other one is the negatively skewed. So the one is which is more toward the right side of your right side, that is negatively skewed, and one which is more towards your positive side, that is the positively skewed. Because ideally we would like to have a distribution which you can see here which is represented by this pink line in kurtosis diagram. So that is a normal distribution. But if, for example, you see that the peak is shifted towards your right, then your data is negatively skewed. And if peak is shifted towards your left, then that is positively skewed. So if the kurtosis is close to zero, then, for example, if the kurtosis is zero, we say that it's close to normal, which means that lower the value of the kurtosis is, you are less departing from normal distribution. So which means that it's good if your kurtosis value is low, or if it's close to zero. As I mentioned, that a negative value indicates a distribution which is more peaked than normal, and a positive kurtosis indicates a shape flatter than the normal one. And a kurtosis value of plus minus 1 is considered very good for most psychometric uses, but plus minus 2 is also usually acceptable. Now, different fields have different norms, and you have to go with the norm of the field. As I mentioned that in my field, organizational behavior, journals are accepting if your skewness and kurtosis are within the range of plus minus 1.5. But for example, if you see the quantitative studies in psychology, those are very strict, or social psychology, sometimes like they want these values to be within the range of plus minus 1. Similarly, for example, if you can see that what are the norms in your field, or the papers which are being published, what are the typical value of kurtosis or skewness which journal editors or reviewers are willing to accept. Okay, so the other thing was the skewness. Again, a value of 0 means that a distribution is symmetric. So which means, again, just like the kurtosis case, if it is close to 0, which means that you have a symmetric distribution. Positive skewness indicates a greater number of smaller values, and a negative value indicates a greater number of larger values. Again, the same rule, plus minus 1 is considered very good for most psychometric uses, plus minus 2 is also acceptable. But again, it varies from field to field. Okay, so I think now we'll go back to the data set. Let me open my Spaces file, and we will see that how we can calculate this in Spaces. Can you see the data file?
Yes.
Okay, that's good. So this is the same data file which was given to you for your assignments, sleep3ed.sav. Okay, now here you can see what we talked about yesterday, all the variable names, their values, and measurement type, and so on and so forth. Now, for instance, and this is the data, and you can see if you look at these dots means that these are missing values. Okay. So now we are interested in looking at descriptive statistics of some of the variables. Okay, now how we would do that? We will click on analyze. As I told you yesterday that almost 90% of the statistical tests are available under this button, analyze. So we click on analyze, and if we come here, which is descriptive statistics. Now, when you click on descriptive statistics, you will find different options. Now, most of the time we use this option explore or descriptives. So, okay, let's use this option descriptive. Or sometimes you can also use frequencies, but the more richer options are available in explore. So explore button has more options. It also tests for normality and things like that. You have also the options which are available in descriptive and frequencies. Those are the subset of the options which you have available in explore. Okay, let's click at explore. Now the same, for example, we are interested in looking at the descriptive statistics for weight. So I click on weight, and if I press the shift key, then I click on height, a general weight, physical fitness, okay, current weight, and then I click on this arrow. Now this will bring these variables here in the next box, which means that SPSS are only going to give me the output for these variables, which I have put in the variable box. Okay. Now, if you click here at options, you will see these options which are related to descriptive. You have option for mean, which is selected by default. So we can just keep it like this. You have standard deviation, which is selected by default, maximum, minimum. If you are interested in variance and range, you can also check those, but that's fine. And I'm also, I'm interested in knowing in kurtosis. So I click kurtosis. I click here skewness. You can also ask SPSS to, that how you want this to be displayed by the variable list, the way you have put in the variable into your box, or alphabetic, or ascending means or descending means. So you can ask SPSS to customize the display as well. Okay, now here if I click on continue. Now, yesterday, I told you that if we click on OK, the output will open in a new window. Now, those of you, who want, now there is another option as well. If before clicking OK, if we click on paste, what would happen? If we click on paste, now SPSS would give me the syntax of this command, and this would be open in a syntax editor. Now here, if you look at this, if like, for example, you are, interested in customizing the code, and you are interested in, for example, if you want to save the code, so the best way is you just click on the paste. It will open into a syntax editor, and you can see that how it looks like. Now, for example, in descriptive, you can see here the variable names. These are the same variables which we selected. Now, if you just want to put another variable, just you click here space, and you just type the variable name, the name which is present in your data file. That would be also included in the output. So here, slash statistics, which means we are asking, SPSS for some statistics. What are those statistics? Mean, standard deviation, minimum, maximum, kurtosis, skewness, and you can see full stop. Now, if you are, flexible, or if you want to, if you are more, easy with the syntax, you can make changes in the syntax and you can run it from here. So how you can run it? You just need to select this, select all, and you click on this green button. I click on green, and you can see that SPSS has opened the output for me in a new window. So this is another way. If you want to customize the code, you can just click on the paste. It will open in a syntax editor, and you can play with the syntax. Okay, so now these you can see the descriptive statistics. For example, the weight of the respondent. Now the first column, you can see the N. Now you can see we have different N for different variables. The reason is that by default, the option which is selected in SPSS says that SPSS has to exclude the missing values. So as different variables have different, different variables have different number of complete cases. So that's why you can see that we have a different N for each variable. Now you can see here, for example, the valid N we have is 235. Now, for example, if you look, weight of the respondent is, this is 249 cases. Minimum value of the weight in our data set is 43. Maximum value is 160. Okay, wow. Mean is 73.3. Standard dev is 15.28. Skewness is 1.0. And this is the standard error of the skewness. And kurtosis is 3.47. Now, if by looking at these skewness and kurtosis, what do you think? The distribution of our values in the weight variable, do you think that these are close to normal, or these are departing from normality, from a normal distribution? Anyone? No one? My question is, by looking at skewness and kurtosis, can you let me know that what would be the shape of the distribution without looking at the frequency distribution for the weight variable? So let's talk about the weight variable at this point in time. If you look here, the weight variable, now we are talking about the weight variable, and we are talking about skewness and kurtosis. So skewness of weight variable is 1.00 and kurtosis is 3.47. So can you make a guess, an educated guess about the shape of the distribution? Okay, now if you remember, we talked about that if the skewness and kurtosis values, if these are close to zero, we can say that our distribution shape is close to normal. And then we talked about that if it is within the range of plus minus 1, we say we are in like the distribution is in a good shape. And if it is, and we are also willing to accept it within the range of plus minus 2. But if you look at this, the weight of the respondent, skewness is 1.00, which is again within our limits, but kurtosis is 3.47, which is greater than 2. Or if we take the cutoff point of 1.5, which is greater than 1.5, which means that we have to do some transformations on this to bring the kurtosis within acceptable limit before we move on to the hypothesis testing part. Now, you can still, do the hypothesis testing without doing any transformations, but in that case, your results might be biased. The reason is because if you're running regression or any other bivariate statistical tool or test, the assumption, the underlying assumption for running those tests is that your data is not departing from normal distribution and it's close to a normal distribution. So from that case, in order to have some reliable estimates or trustworthy estimates, we have to transform it. So we'll talk about this, that how we can transform it later. But as of now, like this is the table which gives you the values which we just talked about, this descriptive statistics. And yeah, okay. So going back, okay. Another point, okay, this is my data file. And if, for example, the last run commands usually appear here. If you 1, 2, 3, click on this 4 box, it gives you all those commands which you performed recently, because we did descriptive statistics now, so this is appearing in the top of the list. So sometimes it's very convenient that you click from here instead of going all the way to analyze and going to descriptive and then descriptive and blah. Okay. Now again, if I go to analyze, I click on descriptive, and this time I'm going to click on explore. So if I click on explore, okay, I'll just put the same variables here independently. So you have to put them in the dependent list in the first box, because this is more powerful explore function, because it also gives you the option of graphical tools. For example, here it tells you that you are interested in only statistics or plots. So the default option is both. So let it be like both. If you go to the statistics, again, we are asking for descriptive. It is by default selected. Keep it like this. The new feature, which is the plot. So if you click on plots, it gives you different options here. So I think one thing which you can do is you can click on this normality plots with tests. You can also click this histogram. Okay, stem and leaf, maybe you can just uncheck this. So we are interested in histogram, normality plots, and box plots, which is by default selected. So if I click on continue, this time I'm not going to click on paste, I'm going to click on OK, so that you know that if you click on paste, it will take you to the syntax editor, but that's fine. So if I click on OK, okay, so it's just running. Okay, now this is the output. So this was the last output. So I'm just going to delete it from here, like plus del, so it's gone. So this will give you the output variable by variable. So our first variable was, for example, if we here on the weight of the respondents. So, okay, let's first look at the descriptive. So if you look at the descriptive, so it is the weight of the respondents. Again, the same mean value, median, variance, standard deviation, minimum, maximum, range, interquartile range, skewness, the same values which we previously looked at, 1.03, kurtosis 3.6, and so on. So you can have the descriptive values for each and every variable here, which you included in your, okay. Then you have another table which is which gives you the results on the tests of normality. We'll talk about this later. Okay. Now this is the histogram. Now histogram tells you the shape of the distribution. Now you can see because once you look here at your skewness and kurtosis, you can make a guess that how your distribution would look like. If you're here, the weight, it's for the weight variable, the skewness is 1.0 and kurtosis is 3.6. So it is positive 3.6. So you can see that that's why it's very tall, peaked, distribution. It's going up here. And so this is how the shape of this is how your values in your data set are distributed as far as their frequency is concerned. Okay, so this is a histogram which gives you the frequency distribution of different values in your data set. If you go down, just ignore this one. Another plot which you are interested in is the box plot. Now this is the box plot. Now the box plot, you can see there's a box and there are two lines up and down. So this middle black line, which you can see here inside the box, that tells you the median value in your data set. For example, here the median value should be, somewhere between, I think 70, because the 75 is up. So somewhere between maybe 70 or 68 or 70. And this is the quartile 1, quartile 3. And any values which are falling above this line, those are potential outliers in your data set. For example, here you can say number 2, number 3, and number 1. So the number 1, which is star 1, that is an outlier, which is far away from the rest of the values. And case number 2 and case number 3, these are basically, the case IDs. So case number 2, when I use the word case means respondent or one row. So row number 2, row number 3, and row number 1, these are the potential outliers for weight variables. Okay, so this is the distribution of the height, variable histogram of the height. And if you go down, we don't see any outlier in height. No, we do have, it's general health. Okay. So, yeah, in height, you don't see any values falling beyond these lines. So, which means that all values are like, we don't see any outlier here. Okay, so this is the distribution of frequency distribution of the general health variable. We go down. Okay, here in general health, you can say that we have case number 150, 89, 117, and 84. These are the potential outliers where the values are on the lower side. So from that perspective, a box plot is a very useful graphical tool which can let you know about the potential outliers in your data set. But this is just like we don't exclude cases based on just these numbers. There are some other tests which we have to run to make sure that these are real outliers. We'll talk about those. Okay, this is physical fitness. You can say that the shape of the physical fitness distribution looks like a normal distribution, but not very far from the normality. And yeah, here you can see no outliers in physical fitness as well. Yeah. Okay, so this is how you can ask SPSS to display like histogram and box plot for you for different variables. Histogram basically tells you the shape of the distribution, and box plot, with the help of box plots, you can identify potential outliers on that particular variable. And apart from that, this table, descriptive table, gives you the mean value, also the median value. So, but we are interested in mean, standard deviation, and skewness and kurtosis. And another important, I think, value, which probably maybe you can sometimes look at, is maximum and minimum. Because, for example, maximum and minimum values, they tell you that you do not have any aberrant values in your data set. Aberrant values are those values which are unusual values and which are not part of the measurement scale, but sometimes due to typing errors or some other errors, you might have those values in your data set. For example, if you are dealing with a Likert type scale, which has values, minimum value 1 and maximum 5 on a scale of 1 to 5, strongly agree to strongly disagree. And if you are having a value of 11 in your data set, which means that is an aberrant value. Probably by pushing 1 while you are typing data, you just press 1 twice, and it ended up in having 11. So by looking at the minimum and maximum value, that also can give you a hint that you do not have any aberrant value in the data set. You don't have any values which fall below or above the minimum and the maximum points available in your measurement scale. So from that perspective, sometimes it's a good idea to look at these minimum and maximum values, so that you can see that these values fall within the measurement spectrum you are using. Okay, good. So, okay, I'm again share my screen. Okay, we talked about this, standard deviation. Okay, so now coming to the data screening part, the one thing which we should look at is the aberrant values. Again, I just mentioned that how you can check for aberrant value is you can look at the maximum and the minimum values in the descriptive statistics table, and that will give you an idea that whether your values fall within the measurement spectrum or not. So if you have values which are below than the lowest possible value in your measurement scale, which means that that's an aberrant value. And if you have a value which is higher than the maximum value available in your measurement scale, which means that's an aberrant value. Okay, so that's easy to do, but it is important to look for these values. Okay. Okay, the second thing is outliers. Now, how you can, now what is an outlier? As we already mentioned, that it's an extreme value on one variable or combination of scores on two or more variables. Because now we are only dealing with univariate statistics, because we are looking at one variable at one point in time. But once you have a theoretical model to test, where you have outliers. Any question? Okay, so now we are talking about the univariate analysis. Now, univariate means one variable at a time. You see that once we looked at, when we looked at the outliers, we just looked at one variable at one point in time. But when we are, running statistical tests where we have more than one variable, which we call multivariate statistics, then we cannot look at the outliers, on each variable at a single point in time. Rather, there are tools available which can give us some indication that whether the multivariate outlier, whether some cases are prone to having a multivariate outliers or not. So that's why when we are dealing with multivariate statistics, we look at multivariate outliers. Okay, and we'll talk about this, how we can, check for those. Okay, now, yeah, okay. So this is what we meant by outliers, and why we are interested in removing the outliers, because they lead to type 1 and type 2 errors. And you know what is type 1 and type 2 error? Type 1 error is like false positive, and type 2 error is false negative. We will talk about this, null hypothesis and alternate hypothesis in the next session when we talk about the hypothesis testing. But as of now, you can just, understand this, that if we do not remove the outliers, we may have biased estimates, and those biased estimates may lead us to having type 1 error or type 2 error, which means false positive or false negative. Okay. Now, the next thing, as I just mentioned, is concerned with detection of outliers. Now, univariate outliers, there are a couple of techniques through which we can check for univariate outliers. Now, one way of doing this is you can inspect the standardized scores in your data set on each variable. And if you are dealing with a data set where the sample size is greater than 80, now the standardized scores should fall between plus minus 3.29. If a case which has a which doesn't have a value of standardized score within the range of plus minus 3.29, now that case is an outlier on that particular variable. And if you are dealing with a small data set where the value of n is less than 80, you have less than 80 cases, so the cutoff value is plus minus 2.5. Okay. And the second way of looking at the univariate outliers is with the help of graphical tools. And we just talked about one graphical tool, which is box plot. So you can ask the SPSS to give you or to display box plot for that particular variable, and then you can look at the box plot and any case numbers which are falling, above or below those lines, which I just showed you a couple of minutes ago. And so SPSS will give you the case number for those cases which are falling above or below the cutoff lines. So those cases are potential outliers in your data set. Okay, I'll tell you that how you can calculate standardized scores. Basically, how we calculate standardized scores. Standardized score is if you a score minus the mean value divided by standard deviation. That gives you the standardized score. So whatever value you have for that particular case or row or observation, you subtract mean from that value and you divide it by standard deviation, then you are going to get a standardized score. And standardized score should fall within a limit of plus minus 3.9 if you have a sample size of greater than 80. Now, for example, let's do this, and then we'll move on to the next part, which is multivariate outlier. Okay, so I'm just going to open that file again. Now, this file, okay, I'll go back to this again. I'm clicking on recall. I click here at the explore. It's not explore. I click here on descriptives. For example, I'm just interested in two variables so that we don't have too many. I move these back. Okay, so I have weight of the respondents and height of the respondents. You can see this checkbox here, which says save standardized values as variables. What I have to do, I just need to check this. If I check this and I click on OK, SPSS would give me descriptive statistics, which you can see here. But apart from that, what SPSS do, SPSS would save the standardized score or the z-score values in my data file. So if I go back to my data file here, if I go to variable view, you can see these two new variables here, which SPSS has created for me, z weight and z height. So z score for weight and z score for height. Z scores are basically the standardized scores. I told you that how standardized scores are calculated. That is the score minus mean value divided by standard deviation. And our cutoff point, because here we are talking about a data set which is greater than 80. And in that case, our cutoff point was plus minus 3.29. So what I'll do, I'll go back to the data view here. I click here on the data view. I go to the data view and I'll see that what are the maximum values I have on z weight and z height variables. Okay, if I scroll it further on the right side. So these are the z-score values which SPSS has calculated for me. So if I click here on the z weight and I ask SPSS to sort it descending. So if I click on sort descending, you can see that this, the first row here, there is only one case which has a value which is greater than 3.29. So 5.6, which means that that is a case for potential outlier. So if I note the ID number is 424 here. Now this I looked at the plus side. Now if I scroll down and go to the bottom, or what I can do, I again click here and I ask the SPSS to sort is ascending. So these are there are missing values on weights. That's why SPSS has not given me any estimate. Now the lowest value is minus 1.98 if you see here, which means that there is no value which is beyond the range of minus 3.29. So on the lower side we don't have any value. So which means that there is only one case here. 424. The ID was 424. If I asked SPSS to again descending, so this is the first case here. ID is 424. Now SPSS case number 1 and ID is 424. Okay, so I'll just note it down that. Okay, now we can just double check this, that whether box plot is going to tell us the same thing or not. So I'll click here on the recall. I go to explore, and this was which way? Sorry, I forgot the name. This was height or weight? Weight. Okay. So I go back here. I go back on explore. I'll just put weight here inside. I'm going to remove the remaining one. Okay. I only have weight. Okay. So I am asking SPSS to display both. I go to plots and I'm not interested in histogram. I'm not interested in normality. I'm only interested in box plot. Okay, continue. Okay, So I click here. So you can see that SPS is also telling me that this case number one. Now this number one is not the ID number which we have in the data set. Like this number one is the row number one. And if we look our data set, and this is what exactly the row number one is, which the case number was, ID number was 424. So row number one. This is what my box plot figure is telling me. The same thing, more or less the same thing, that number one is far from other values. So that is an outlier, and that's why that is marked with a star, because it is very far. We also have row number 2 and 3, but those are very close. And when we look at the standardized scores, these two are not identified as outlier. So which means that we can still keep 2 and 3, but 1 we have to remove if we are running some analysis with this variable weight. Now let's check our second variable, which was scores on our second variable, height. Now these are the scores, standardized scores for height, Z height. So I would ask SPSS to arrange these in descending order. Now the highest value is 2.8. Again, we are not deviating from the cutoff value here, which was like plus 3.29, which means that on the positive side of Z scores, we are good with this variable height. Now I would ask the SPSS to arrange it ascending, and we can say that the lowest value is minus 1.9. Again, this falls within the cutoff value of minus 3.9, which means that we do not have any potential case of outlier on height variable. We can double check this with the help of box plot as well. So I click here on the recall. I go to explore. I remove this weight. I put height here. And okay, I ask SPSS give me both, and plots. I'm asking, okay, only this box plot. If I click on OK, if you go down here, you can see this is the box plot for the height in centimeter. And this box plot is not telling us that there is any row in your data set or any case or any observation in your data set which is a potential case for outliers, which means that on the height variable, we are good to go. Okay, so this is, let me just move this so that we have a clean file. Okay, so this is how we check for univariate outliers. And the second thing is the multivariate outliers. Now, checking for multivariate outliers is a bit tricky, not that tricky, but we have to follow certain steps in order to check for multivariate outliers. Now, for multivariate outliers, we ask SPSS to calculate Mahalanobis distance for us. Now, basically, what is a Mahalanobis distance? Mahalanobis distance is now what SPSS does in the background, because multivariate outliers deals with outliers on more than one variable. For example, if you are interested in looking at that whether a case, an observation, or a respondent or a case is a potential outlier on 3 variables like height, weight, health rate, or some other fourth one. So what SPSS will do, SPSS would calculate the joint mean for all these variables, and then would measure the distance of each observation from that joint mean. And that distance is known as Mahalanobis distance, because now we are not dealing like in a two-axis plane. Like if you're having with the 4 variables, you need to have a joint mean and a joint calculation keeping in view all those variables. So we ask SPSS to calculate Mahalanobis distance, and SPSS would calculate the Mahalanobis distance for each case or observation for us. And then what we do, we would compare those scores with a chi-square distribution. So, and then we will calculate the probability, because we are not sure that whether whatever Mahalanobis distance SPSS have calculated, whether that distance is statistically significant or not. It's the same thing, we talked about yesterday when we were looking at the correlation coefficient, that whatever the correlation coefficient does not make sense, and we would not interpret it unless it is statistically significant. Now, same is the case here. So once we calculated the Mahalanobis distance, we would also calculate the associated probability. And I'll let you know that how we do that. And once we calculate that, which means then we would be able to, have a p-value for that. And by looking at the p-value, we can make a case that whether this Mahalanobis distance is statistically significant or not. Okay, so now I would tell you that how we do that. Okay, let me go back to the data file. Okay, so this is the data file. Now, for instance, okay, let me look at the variable view. For instance, because as I told you that this Mahalanobis distance is used to calculate multivariate outliers. And we are interested in knowing the multivariate outliers, interested in finding the multivariate outliers only when we are dealing with multivariate statistics. Now, for instance, one of the multivariate statistics is regression. Now, regression is, for example, where you have a dependent variable and you have like more than one or only one like independent variables. Now, for instance, here we have hypothesized that the health rate is being predicted by weight, height, weight rate, how many alcoholic drinks a person takes, how many caffeine drinks a person takes, and so on and so forth. For example, this is our hypothesized model. So basically, we have like 3 or 4 variables, and we are interested in knowing that whether before going for our main statistical tests, we are interested in knowing that are there any multivariate outliers or not in our data set. So how we will do? We will click on analyze. We will go down. We will click on regression. After regression, you will click here on linear. Okay. Now here you have 2 boxes. The first one is the dependent variable and the other one is the independent variable. Now, for example, as I just mentioned, that general health, this is my dependent variable, and on independent variable, I say that weight of the respondent, physical fitness of the respondent, cigarettes per day, alcoholic drinks per day, caffeine drinks per day, sleep per weeks per night. So maybe these are how many variables we have now here as independent? 1, 2, 3, 4, 5, 6, 6. Okay, 6 dependent variable or independent variable and 1 dependent variable. Okay. So now if you click here at the statistics part, you can see that SPSS is giving you different options. Don't do anything here. Uncheck this. If you click here on the save part, you would have different boxes here. And if you look here at the, if you see here at the distances, this second, group of parameters, you have Mahalanobis. So I would just check Mahalanobis here. Okay. Now, whenever we check something from the save box, it's not only related to the regression, which we are doing here, trying to do here. Rather, in most of tests which you will do in SPSS, SPS gives you the option of save. So whenever there is save, you go to the save. Whatever options you check in the save box, those values would be saved in your data set. Okay, if I click on the continue, okay, you just leave all these options as it is, you will keep, this method here as enter it is, and you click and okay. Now forget about this, the values which are shown in the output box here. We're not interested in those. So I'm just going to remove this. My interest is I would go back to my data file, and you can see here a new variable, which is MAH_1, and the label is Mahalanobis distance. If I go to my data view, here I would see MAH_1, and I would see Mahalanobis distance values for different. Now, wherever there is a missing value on one of these 6 variables, independent variables, which I put in the regression box, SPSS will not calculate the Mahalanobis distance for those. And that's why it is important to treat missing values at first place, so that you don't get these dots when you're running your analysis. Okay. Now, okay, if I ask the SPSS to do descending, you can see that there are these 2K, number 1 and row 2, and even row number 3. They have the high Mahalanobis distance values like 22, 20, 13. And then, there's a significant drop, the number from 13 to 9. And then, 8, 8, 7, 7. So these are pretty close, 9 onwards. So the first 3, 22, 20, and 13, I suspect that these cases might be the potential outliers. If you go here, you can see the ID numbers 45, 41, and 534. You can see this, 45, 41, and 534. These might be potential outliers, but I cannot be sure until and unless I have the p-value. So because I'm not sure that whether these higher values 22, 20, and 13, whether these are statistically significant or not. Now for that, I have to calculate the associated probability of this Mahalanobis distance in order to make my judgment call, in order to to be sure that whether these cases are multivariate outliers or not. Now, how to do that? So I would go to transform, and then I would go to compute variable. Okay. If I click on the compute, now basically what I'm trying to do here, I'm trying to compare these distances, the probability of these distances with a chi-square distribution, and then the SPSS would calculate the associated probability. So maybe I write here prob Mahalanobis distance MD. So target variable means whatever name I give here, that would be the name of the variable which SPSS is going to create for me. So I can give any name. If I give like PR underscore Mahalanobis distance MD, that's fine. So I can give any name, target variable. Now here in numerical expression, here on the right hand side here, SPS has some built-in functions. So for instance, I don't have to write the whole formula. I can just pick that function and ask SPSS to run it for me, and SPSS will give me output. For example, I'm interested because here in comparing it to a chi-square distribution. So chi-square distribution starts with C. So here I would press C. So this is CDF. No, this is not. Yeah, here. So this is CDF.CHISQ, chi-square. So I would click on this, then I would click on this arrow, and I'll bring it up in the numeric expression. Now here you can see that in the bracket, SPSS is asking me for 2 values. There are 2 question marks. Now the first question mark is which specific variable I want to compare with the chi-square distribution. And the variable for me is Mahalanobis distance, which in my data set is MAH_1. So here I would type the name of the variable which I want to compare with chi-square distribution. And after this comma, the second question mark, I would enter, it's basically the degrees of freedom. Now, you don't have to wrap your head around that what degrees of freedom are, but as just a rule of thumb, you would here mention the number of variables you have, which based on which you have calculated Mahalanobis distance. So we had 6 independent variables. So only the independent variables, not taken into considering the dependent. So we had 6 independent variables. So I would just write 6. Okay. And then I would ask SPSS, if I click at the OK, SPSS would run this command. Okay. So now if I go back to my data set, I would find this new variable PR, which I created, PR underscore MD, probability of Mahalanobis distance. Now I can go to the variable view and I can change these decimals to maybe 5 so that we have a better, okay. Now here you can see that these are the probabilities. And last time I told you that if the p-value is less than 0.05, we consider that this is significant. But for Mahalanobis distance, we want to be like 100% sure. So that's why we look at the p-value which is less than 0.001. So if I just arrange these p-values in ascending order, I would see that are there any p-values which are less than 0.001? Okay. So we don't see any p-value which is less than 0.001. So the lowest p-value we have is 0.004, which means that the Mahalanobis distance which we calculated, and those distance like 20, 22, 13, which you can see here under this variable name, are not statistically significant. So based on this analysis, none of the cases in our data set is a case of multivariate outliers, because we don't have any p-value which is less than 0.001. Okay. Now let us, okay, I'm just going to delete this. Let me delete this as well. Z wide, Z height. Okay, let's do one more time. Okay, if we, sorry, not compute. We go to the same linear regression, and now we reduce the number of variables. We have weight. Okay. And maybe we include height. So now we have 3 variables, okay? So I just click on the OK. Don't look at this output. I would go to my data file back. I would have this Mahalanobis distance. If I arrange it in a descending order, I will see we have 41, 15, 13, 13, and so on. Now again, the next step would be I calculate the associated p-value. The same way, I will go to the compute variable. Again, same name, PRM, or any name which you would like. It's the same. Now, do you think I have to make some change here? Anyone in this expression? Let's see who is attentive in the class. Yes, excellent. So we have to change it to 3 because now we are dealing with 3 variables. So instead of 6, we have 3 values. So I'll just put here 3. I click at OK, and I would go back to my data file. I would have these probabilities here. So it's up to 2 decimal places because we are interested in 0.001. So I will make it bigger. I'll go to the variable view. Here on decimal, I'll make it like maybe 4, 5, anything you would like, but anything greater than 3. I'll come back to the data file, this data view. Here I click here, and I ask the SPSS to arrange it, ascending. And if we go down, wow. Now, do you see any cases Any potential cases for the outlier? How many cases do you think? So these are the associated probabilities. Sorry, which are arranged in ascending order. So do you think that, do we have an outlier here? Okay, so Dr. Azam is saying that the case number 39, this is 39. If we scroll here, yes, because you can see that the probability is P is less than 0.001. And here if like the p-value is less than 0.001, which means our Mahalanobis distance is significant, this value is significant, and that's the potential case for outlier. So this is and here the p-value is 0.00022, which is less than 0.001. So this row number 39 is a potential case for outliers, multivariate outliers. So you can see that we changed the number of variables and we got a different result, which means that, again, it goes back to the same point that what in the background SPSS does, it calculates a mean value for all the variables. And when you change the number of variables, the mean value is changed. So this is how we identify the multivariate outliers. I know it might be a bit heavy, but this is how it is. You have to practice. More you practice, more you learn, and more you play with the SPSS software, more you would learn. Okay, so this is how we detect outliers. Okay, the third thing which is part of data cleaning is normality. As I mentioned, that most of statistical tests assume that our data is normal. So we are interested in looking at in running some of the statistics to see that whether our data is normal or not. Now, previously I told you that we look at skewness and kurtosis values to make an educated guess that whether our data is normal or are we departing from normality. But apart from that, there are two tests available in SPSS, which like SPSS can, like by looking at the output of those tests, we can be sure shot that whether the data is, our distribution is normal or not. Now, again, the multivariate normality is the assumption that each variable and odd linear combination of variables are normally distributed. Okay. We typically look at skewness and kurtosis values. We also look at histogram with normality curve. I'll show you that how this looks like. And there are two tests which SPSS, we can ask SPSS to perform those tests for us. These are Kolmogorov-Smirnov test and Shapiro-Wilk test. Now, Kolmogorov-Smirnov test that gives us D statistics, and Shapiro-Wilk test gives us W statistics. Now, if you have a sample size which is greater than 2000, which means for bigger sample size, we use Kolmogorov-Smirnov test. And for samples which are smaller than 2000, we use the output from the Shapiro-Wilk test. If the value of W is equal to 1, which means the data is perfectly normal, which means if the value of W is more closer, the value is more closer to the 1, the more closer our data or distribution of our data would be close to a normal distribution. I'll show you that how we can do this and how to interpret output. Okay. Now this is again a null hypothesis and alternate hypothesis. I'll not go into details, but I'll talk about this in the next class. Now for these tests, our null hypothesis is that the observed distribution fits the normal distribution, and the alternate hypothesis is the observed distribution does not fit the normal distribution. Now your null and alternate hypotheses are always contradictory, and based on your statistical results, you accept one of these hypotheses. Sometimes we do not make a null hypothesis explicit, but that is somewhere at the back of your head. and you only write your alternate hypothesis. Now, for example, we look at the p-value, and if the p is less than 0.05, we reject the null hypothesis and we accept the alternate hypothesis. So this is what is the use of the p-value is, that if the p-value is less than 0.05, we accept the alternate hypothesis and we reject the null hypothesis. This is the rule. This is how we interpret the p-value. Okay, now let me go back to my data file and run these tests for you. Okay, this is my data set, the same sleep3ed. Okay, I'll go to this analyze, I'll go to descriptive, I'll go to explore. Now, for example, I'm interested in looking at the height and maybe weight. We can also look at these two variables. Okay, I go to the statistics, you will have descriptive, same things. If you go to the plot, I can ask SPSS to do the box plot. Okay, but we already looked at the box plot, so I'll put none here. I'm not asking SPSS to prepare to draw the box plot for me, but I'll ask the SPSS to draw the histogram, and I'll ask SPSS, I'll check this button, normality plots with tests. Okay, I'll click on the continue, I click on OK, and if you go down, now you will see this table, tests of normality. Now, because we checked a box there, which was normality plots with tests, so that's why SPSS is giving us these two tests, which we just talked about, Kolmogorov, Smirnov, and Shapiro-Wilk test. Now, these two tests are, like these are dependent on the sample size. If we have a sample size of less than 2000, we look at the Shapiro-Wilk test, and if it is greater than 2000, we look at Kolmogorov-Smirnov test. Now, if you look here at the Shapiro-Wilk test, you will see that the test statistic is 0.97 for the height variable, and for the weight, it is 0.95. Now, if you look at the p-value for both the tests, it is 0.001. Now, which means that this Shapiro-Wilk statistic is significant, right? Because this is less than 0.05 within 95% confidence interval. And if you look at the value for the weight variable, again, that is less than 0.05. Now, what did I tell you a couple of minutes ago? That if the p-value is less than 0.05, which hypothesis we reject? Null or alternate? Anyone? Yes, true. If the p-value is less than 0.05, we reject the null hypothesis and we accept the alternate hypothesis. Now, these were our null and alternate hypotheses as far as Shapiro-Wilk and Kolmogorov-Smirnov tests are concerned. Our null hypothesis is the observed distribution fits the normal distribution. And our alternate hypothesis is the observed distribution does not fit the normal distribution. Now, what do you think? Do you think that our data is normal, or our data follows a normal distribution? Based on, now you know that what is the null hypothesis and what is the alternate hypothesis, and you know that the output from the SPSS. Now this is the output. Okay, let's look at the Shapiro-Wilk test. For both height and weight, it is significant. The value, the p-values are significant, which means less than 0.05. Now, which means that we have to accept the alternate hypothesis, right? And if you look at our alternate hypothesis, it says the observed distribution does not fit the normal distribution. That's why, it is important to know that what are your null and alternate hypotheses. This is not the case that whenever if p-value is less than 0.5, and which means that we are good to go. If p-value is less than 0.5, we would accept the alternate hypothesis. And in this case, the alternate hypothesis is the observed distribution does not fit the normal distribution, which means that for both of our variables here in the output, height and weight, these are not normal. The distribution is not normal. Okay. And if we go up, we can see that height is skewness is 0.34. It has a positive skewness, and kurtosis is negative, minus 0.6. And for weight is both skewness and kurtosis are positive. But as I already told you, that if the values are within the range of plus minus 1.5, we are good to go because we rarely find any data set in social sciences which is normal. So here for the height, values for the skewness and kurtosis are within the limit of plus minus 1.5. So we can proceed with our main analysis. But for the weight, you can see the kurtosis is 3.5, which is too high. So maybe we need to do some treatment with this variable in order to make it close to normal. Okay. Now, if you go down, okay, so this is the height, for instance. There used to be an option where you can ask SPSS to draw the normality curve on this. Here, yeah. It opens in a new window and normality curve is that. Yeah, show distribution curve. Yeah. So normal. So you can ask the SPSS to draw a normality curve for you. So this is the shape of the normal distribution. If this is distribution, so this is the shape of the ideal distribution. You can see that these values which are, falling like above this normal distribution range. Now, so you can see that how, but again, this is close to normality. You can see the height. And if I go to the weight, if I click here, I asked the SPSS to, sorry. How did I do that, the earlier one? Sorry, I forgot. Double click. Yeah, this one, sorry. Okay, so you can see that this could have been the shape of the distribution if it would have been perfectly normal. Okay, so now the next question is, if my data is not normal, what I can do with it? Now, as I told you that for the weight variable, the kurtosis is plus 3.5, which is quite away from my cutoff value of 1.5. So I need to do something with the weight variable so that the shape of the distribution becomes closer. Yeah, we need to transform. So how we do that? These are some of the rules. For example, if the shape of the distribution is it's positively skewed and shape is like this, you have to do a square root transformation. If the shape is like this, you have to do logarithmic And if the shape is like this, you have to do inverse. And for negatively skewed data, like for example, these are, you have to reflect and then transform. So first you will calculate a reflection of that variable, and then you will do square root on those values. Okay, so now I can show you that how you can do this in SPSS, for instance. Okay, I'll go back to my data file. It's pretty easy to do it. You don't have to worry about that. You'll go to the same transform function. You'll go to the compute variable. Okay, so I'll just remove whatever I have here already. I'll just delete this. For instance, we are interested with the weight variable. Okay. Now, if you want to do the square root, so just type any name, maybe SQRT underscore WT. That's the square root of weight variable. Now, here you will find the square root function. I just have to press S. Yeah, here, SQRT. I select SQRT, I press on the arrow, it will come here. Now, this is asking you a question in the bracket that which variable you want to do square root. So if you want to do the square root for the weight, you put in here. If you want to do square root, of height, you will select height and bring it in here. So I'll just, if I press at the OK, you will find a new variable in your data set, SQRT underscore WT. That is the square root of the weight variable. Now, similarly, you can do other transformations. For example, if you are interested in knowing in inverse I and B. Now, inverse is, it's pretty easy. 1 over its weight. If you bring weight in here, so inverse 1 over weight. If you click in OK, you will see a new inverse in your data set. And if you are interested in doing the logarithmic, so maybe I'll log underscore weight. Remove this. I'll just search for the log function. I'll just press L. Yeah, log to base 10. So log, bring it in here, and I'll wait and click on OK. So if you go to your data set, you will find log of weight. So this is how you can use logarithmic, inverse, and square root. How do we do the inverse? The reflected. How can we create the reflected variable? Now, the reflected variable is created. It's very easy. It's the maximum value plus 1 minus the value on that specific case. For example, we are interested in creating the reflect variable for weight. So let me see that what is the maximum value on weight. I can do it from here, weight and descending. So the maximum value for weight is 160, which means that if I want to create a reflected variable for weight, what I would do, maximum value, this is 160 plus 1, which is equal to 161. So 161 minus value of weight at that particular case. So again, I will go to this compute. It is reflect weight, and I would write 161 minus, because from where this 161 came? This 161 came 160 plus 1, okay, maximum value plus 1 minus weight. 161 minus weight. If I click in OK, so if you go back to your data, you will find here the values here. And then, whatever is written here, that for negatively skewed, you have created a reflected variables. So you have to do the square root on this reflected values. If 160 is an outlier, we cannot use it. So we have to remove it. So the last part from today's session is dealing with the missing data, which is very important. Now, some of the traditional ways of dealing with handling missing data is list-wise deletion, which means like if you have missing value on one of the case, you just remove the case. But as I told you initially, that if you follow this way, you are going to lose a big chunk of your data. So we don't recommend this, and this is not a recommended approach. But if you have more than 50% of missing information on any case, you can exclude that. Now, how you can calculate that how many values you have missing on each variable, or not variable, sorry, on each case. Now, if you run the descriptive statistics in SPSS gives you the missing values on each variable, but not the case. When I'm using the word case, it means I'm talking about the row. I'm talking about the respondent. So for example, one row is your one case. So if we have a data set of 200, we have 200 cases here. So SPSS does not give you by default that the number of missing values in that particular case. So we have to do a bit of calculation to calculate that. One way is like just by eyeballing, but if you have a big data set, it would be quite tough. So how we can do that? I'm just going to show you. You go to again to compute. Okay. I'm interested in number missing. So number missing in that particular case, on each case. So there's a function in SPSS which calculates the missing values on each case, and then the name of the function is nmiss. So I'll just press n from here. Yeah, here you find this nmiss. So I'll bring it up here in my numeric expression. Now in question mark, I want SPSS to give the range of entire variables on that case. For example, if you are interested in only counting the number of missing on a select number of variables, then you have to mention the name of those variables. But if you are interested in counting the number of missing on all the variables in each case, so what you will write, you just look at your variable view, and your first variable name is ID, but we are not interested in knowing because ID we know is not missing because we have given the ID numbers. So I'm interested in knowing the missing values, counting the missing values from variable name sex, SEX, space 2. What is the last here, which I want SPSS to calculate is impact 2, because these Malanobis and probabilities, square root, and this is what we calculated. So impact 2, IMPACT 2. So this to this, like sex to impact 2, which means SPSS would count the number of missing on all the variables starting from number 2 sex to the last, which is impact 2. Okay, if I click here at the OK, and if I go back to my data file here, you would see that SPSS has created a new variable num missing, and this one is what? This one is the number of missing values on this case. For example, if I select here and if I go, you can see that this is missing 1 here, and if I go further down, I don't see any other missing, and that's why we see that SPSS has calculated 1. Now, why we do this? Because we want to see that the cases which have more than 50% missing values on more than 50% of the variables, probably we should exclude those. Now, if I arrange this in descending orders, you see that the highest number of missing are 7. So we have like, if you're here for case number 79, 91, 241, ID numbers, those have 7 missings, then 6 missings, 5 missing, 555, 444. So this gives you a fair idea. So maybe you would want to delete like all those cases which have 5 or more missing values. And for the rest, you can do like you can do the imputation. You can replace the missing values with a desirable number. Okay, so this is how you calculate the number of missing values on each case. Okay, going back to my slides. Some of the other ways are, doing mean substitution, that you calculate the mean of that variable and substitute it, but this is not advisable. Another way is expert judgment. Now, for example, if you have 5 questions, here I'm talking about the questions which typically I use in my field. The question have multiple items. A construct or a variable has multiple items or questions. And sometimes those questions are similar to each other. So if a respondent has missed one of those questions, then if I take the reading of a similar question and replace it with the one on which there's a missing value, but that sometimes you can't do this if you have a lot of missing values and it's tedious. So yeah. Now the most widely used method, and this is an advanced technique, is multiple imputations. I'm just going to give you a brief overview of multiple imputations, and then you can do it by your own. We're not going to do it here, but I'll tell you that what this is about. Now, what multiple imputations does? Now, in multiple imputation, what SPSS does? SPSS runs simulation and make patterns in the missing data and then replace the missing values. Now, for example, SPSS would try to identify the similar cases which are without missing to the one which are with the missing values. And if the attributes of those cases are similar to the one where you have missing values, SPSS would replace those missing values by taking values from the cases which are similar to those with the missing data. So basically it runs simulations, iterations at the back end to try to, so this is an intelligent way of replacing missing values. And before doing that, SPSS, it analyzes the patterns of the missing values, that whether the missing values are systematic or random. If the missing values are random, there is no pattern, there's a different way to impute it. And if those are systematic, we see a pattern there, then SPSS uses a different way. Now, how you can do that? Let me open my data file. Okay. Now you go to this analyze, and in analyze down there, you have this missing value analysis. And then down there, you have multiple imputation. Now, because as I told you that multiple imputation is the most widely used method. So first you will analyze the patterns, because after making this conclusion that whether your data is missing at random or missing systematically, then you can use this second option, impute missing values, because in impute missing data values, you have 2 options. One option is related to if data is systematically missing, and the second option is related to if data is missing at random. So you have to select one of those options, and you can only select one of those options if you analyze the pattern first. So if you go to the analyze pattern, and for instance, if we are interested in all, I just Control A, put here, and you click on OK. So SPSS would give you this output. Now this is the overall summary of missing values. Now this, blue is the complete data and red is the incomplete data. Now, 4 variables, they have the complete data, and 23 variables, they have missing values. This is by variable. This is by cases. 4% of the cases, or 12 cases, those are complete without any missing value. And 259 cases, they have one or more than one missing value. And here, like, these are per values, that how many values are missing. Okay. Now, this is an important piece of information, this missing value pattern. Now, if you look at this graph, you can see that these red are the missing values. On the x-axis, you have the variable names, and on the y-axis, you have the pattern. Now, we don't see any pattern here, like we don't see any design. So this means that this missing values do not follow an appropriate pattern, that if it's missing on one, it's also missing on the other, which means that we can, there's another statistical test, like Little's test, which you can use to also assess it. But this, I'm just giving you an orientation here, and then you can, those of you who are interested in learning this, they can do it by their own, because this is important. I think all of us, they have missing values on our data sets, on our surveys. So from here, you would conclude that whether the data is missing at random or missing systematic. Okay. Now, by looking at this chart, we concluded that there is no systematic pattern, and we are saying that the data is missing at random. Now you will go back to the second part here. Sorry, multiple imputations. And so after analyzing pattern, now you will go to impute missing values. So for instance, if I select Control A, I put all the values in. Now here SPSS asks you that how many simulations it should perform. So you can ask the SPSS to do, the default is 5. So you can keep it like this. And you can also ask the SPSS to save, because you do not want to disturb your original file. You can ask the SPSS to save this information in a new file. So you just give it a name. For instance, E3ED dot missing replaced, like this. Okay. And here, like, you have method, automatic and custom. Now, if your data is missing at random, you will go with this automatic. But if your data is missing systematically, you would choose custom. Okay. For example, here you can read the description. It says this method is suitable. This method is suitable for data with an arbitrary pattern of missing values, like this. But we will just go with whatever it is. Automatic. You can also put some constraints like that in iteration, what can be the minimum and maximum values, like SPSS has to replace values within those. So you can always do that if you have a scale range. For instance, if you are dealing with a Likert scale or some other way you have a range, you can restrict SPSS that SPSS has to be within that limit while running the iterations. Yeah, imputation model and descriptive statistics with imputed values. You can also ask SPSS to give you output that what are the descriptive statistics when the missing values are replaced. Okay, so this is how you can run it. So I would stop here, and before we leave, I would encourage you that you go back to your this case, assignment case, and please do the remaining question. Now, for example, analyze, question number 1 says, analyze the structure of missing values for all variables. Your analysis should include following things: count number of missing values in each case and record this value. It's not value, in a new variable count missing. Which method will you use to replace the missing values? Justify your choice. So you can always go back to looking at the pattern, and then you can see that which one you are using. Identify outliers for all scale variables. Okay, this is easy to do. You will do it. Do a univariate analysis of following 8 variables. This was given to you yesterday, so you don't need to do it again. Create another variable, which is a multiplication of scores on weight and height variable. Name the variable as VHE. It's very easy to do. You will go to the compute variable, you will write the name WEHE, and you will multiply weight, multiply height, and you will get a new value which will be stored in your data file under WEHE variable name. Make 3 categories of question. How many standard alcoholic drinks do you consume on an average day? Alcohol. Store those into a new variable named alcohol.cat. We didn't do it in the class, but you can try it out. You have Google with you, you have YouTube. So try to do this. And if you don't, if you're not able to do it, we can talk about it in the next class. Okay. If the distribution of these variables, weight, height, health rate, fit rate, weight rate, qual self, impact 1, impact 2 is departing from normality, use appropriate transformations and again reassess the shape of the distribution by using graphs and relevant statistics tests and compare the new distribution with the one without transformation. This is a very useful exercise. This will give you an idea that after transformations, do you see an improvement in the shape of the distribution, or do you see an improvement in kurtosis and skewness statistics, and calculate and interpret the correlation among following variables. I think we didn't do this, but it's very easy to do it. For example, you can go to analyze, you can go to correlation, and in bivariate, we did this yesterday, bivariate, put the variable names in here, keep it like this, two-tailed, Pearson, keep it like this, click OK, and this will give you an output, and you can see that the one which are 2 stars, you can look at the p value where p value is less than 0.05. These are flagged. So you can do it. I'm pretty sure you can do it. Okay. So please finish this assignment, because if you do not practice, you will not learn. This is the more you practice, more you play with the spaces, the more you will learn. Okay. Thank you very much. Sorry for keeping you like 17 minutes over and above the class time. If you have any question, please feel free to ask. If not, you may leave, and inshallah, I'll see you tomorrow.
I think there are no questions. So thank you, Dr. Abdul Karim. Thank you all for attending, and we hope to see you tomorrow.
Inshallah. Okay.
Inshallah. Thank you. Thank you very much.
Bye.